All right. Well, we're starting to get into more of the heart of stuff now. So you had, this is so low. You had your first weekly assignment. If you haven't turned it in yet, I'll still take it, but I will try really hard to get that graded by Friday because you have the first quiz today. That's not a big deal, but the first exam is next week in this class. Okay, so exam 1 is Wednesday, what would that be, 28th? If you can't make it to this class, but you can make it to the Thursday class, that would be fine too, by the way. So I'm going to try to make sure I get your weekly assignments graded so you have time to look those over, see what kind of stuff, if I took off points for things, what kind of things I'm looking for, because I'm going to grade those the same way that I grade the exams. The things that are important to me on the weekly assignments are the same things I'll be looking for on the exams. And for topics, let's do everything up to vectors. So I'm going to start talking about vectors today. I gave you a lecture video on those, but that's not going to be on the test. Okay, so it's all the stuff up until then. So everything before vectors. Okay, yes?
Are we going to have stuff from the lab?
No. Oh, that's a good question. Nothing on the labs will be in the exams because we're also going to have separate lab exams that'll cover that stuff. When? I think there's still 2 or 3 weeks till the first one of those, probably 3 weeks. It's on the syllabus, but I don't remember off the top of my head. So the exams are going to be like the daily problems and the weekly problems. Like if you understand the thought process for how to do all the daily and weekly problems that you've gotten, then you'll be good for the exam. Yep. Any other questions? So I'm just going to start in with new stuff, but this is not going to be on the test next week. Yes?
Oh, I just have a question.
Yeah.
Number 9.
Uh-huh.
9C. I used 2 different equations. Like, I was confused. I didn't know how to do that.
Yeah. Oh, okay.
So I did the acceleration. One
Oh.
equation for the acceleration going up and one for the acceleration going down.
That's great.
Okay.
Yeah, that's
It ended up, when I looked at the answer, it worked, but I didn't know how you did that.
Can I just show the way I would do it? And was there no solution to it online?
There was. Yeah, but
Okay, but it didn't make sense to you as much as the way you did.
Quadratic Formula.
Oh, okay. Oh, okay.
Yeah, you didn't.
All right. Let me just look at that real quick. By the way, anybody who has a programmable calculator, if you pull me aside during lab, if you don't have quadratic formula in your calculator, I can punch it in about a minute, and then you never have to think when you do quadratic formula again. Okay, 1D particle kinematics. No, 1D. Number 9. So how long does it take for the rock to hit the ground? You throw it up into the air. So you did one equation to see how long it took to get to the highest point, and then separate equation from the highest point down to the ground, and then that's smart. Yeah, that works fine. Yeah. Yeah, for sure. Okay, right. That's great. Let me just show you how to do the quadratic form, how it would look in the quadratic formula on that. So 1.535. Oh, does anyone have in front of them like the conversion from 35 feet per second? I could just do it, but I don't have a calculator with me. Okay. So number 9, C. So this thing's thrown up into the air. The height is, what was it, 1.5 meters? And its starting speed is 10.66 meters per second. Okay, so how long does it take to hit the ground? So I'm going to choose my 0 position to be on the ground, positive direction up. Time equals 0 is going to be the instant that it's launched. Time final is going to be the instant right before it hits the ground. So we're trying to calculate TF. We know acceleration is negative 9.81 meters per second squared. The initial position is 1.5 meters. The final position is 0. The initial velocity is positive 10.66 meters per second. And the final velocity we don't know. And so the equation we're going to use is P final is equal to P initial plus V initial time final plus 1/2 A TF squared. So 0 is equal to 1.5 meters plus 10.66 meters per second times TF. And if you combine the 1/2 and the negative 9.81, that's minus 4.905 meters per second squared TF squared. And so for the quadratic formula, the A for your quadratic formula is what you're multiplying by the variable squared. So this is A. The one multiplied by the linear term is B, and the constant is C. And the quadratic formula, and you have to set it up so it's equal to 0, but we already have that in this problem. So it says negative B plus or minus square root of B squared minus 4AC all over 2A. So I think I told someone last week, you don't have to keep if you're going to use the quadratic formula in a problem, you can forget about the units. That's the one time that you can do the calculation and not worry about the units. So negative 10.66 plus or minus square root of 4.905 squared. That negative is
it's b squared. So
b squared. Thank you. You're right. 10.66 squared minus 4 times a, so negative 4.905 times 1.5. Take the square root of all this, all over 2a, and a is negative 4.905. And so you'll get two answers for this. And just like with the velocities, when you get two answers, when you take the square root of a variable and you get a positive or negative answer, you have to think physically about what the positive and negative mean to choose the right answer. In this case, you're going to get a positive and a negative time. It's easy to choose if you get a negative time. That we don't ever have those. So you can throw that one out. That's just sort of mathematical artifact. That's not a real thing. And the positive time is the one that we want. So our answer is positive something, negative something else, we don't want this one, we want this one. Okay, so let's start talking about vectors. So we've been doing one-dimensional kinematics up until now. In 1D kinematics, we have had quantities that have direction and other quantities that don't. So quantities that have direction the main one we've been using are position, velocity, and acceleration. A quantity that doesn't have direction is speed. But there's a relationship between the speed and the velocity. The velocity is just the speed with the direction added onto it. So if an object is moving in the negative direction, with a speed of 5 meters per second, that means that the velocity is negative 5 meters per second. So that's how you show direction in one-dimensional kinematics. We're about to start doing stuff in 2 dimensions. So in 2D, we need a new way to indicate directions. So if this is 1D, so 1D is an object moving along a line, okay? And let's say this is the object that you're looking at, okay? An object at that location only has two choices of where to go, okay? And so if you choose your positive direction to be this way, then positive and negative are enough to indicate the direction wherever it goes. You know, you're either going in the positive direction or the negative direction. But in 2D, where you can move all the way around a plane, there's no way to use signs to indicate all the options that you have at a point. You know, like at a single point, you have infinitely many choices of where to go. And positive and negative are not enough to do this anymore. And so that's why we're introducing vectors now. The vectors are going to take over for the directional quantities when we go to 2 dimensions. Okay, so what is a vector? You can think of it as just an arrow. So think of it as an arrow with a length and a direction. So if this was a vector, you know, I could have drawn that vector any length. It could have been half that long or whatever, twice as long. The direction is the direction it's pointing. And the length that I draw it tells you something important about that quantity. A vector has two properties. A vector. And by the way, this is like exactly the kind of thing that that I put on quizzes, tend to put on quizzes, not on the one today, you know, obviously. But so a vector has two properties, and those are direction, which is just where it's pointing, and magnitude. And that's the length of the vector. Length. And by the way, notice that our directional properties, position, velocity, acceleration, in one dimension, they had these things too. So like when we've been talking about position, velocity, and acceleration, those have kind of been vectors. They've done what vectors do. They just only did it in one dimension, and now we're moving to bigger space. So all directional quantities will be vectors in 2 dimensions. And in 3D also, although we're not going to do any calculations in 3D. A lot of this stuff really isn't much different in 3D than it is in 2D. And so these are going to be, the most important ones are going to be position. And to indicate something's a vector, you draw a little arrow over the top. So position, velocity, and acceleration. And we're going to talk about those largely in the same way that we have been in 1D, but they just are going to have this different mathematical form. Okay, so if a vector is an arrow, okay, think of this thing as a vector. Once you choose a coordinate system, a vector can be represented by its components. So if this is the vector that you're thinking about, okay, and this is the coordinate system that you're using, then the components of that vector are how far you have to go along the x-axis plus how far you have to go along the y-axis. So this is the x component, and this is the y component. To calculate those, to calculate the components, so let's say that this vector has a length L. The first step is put the tail of the vector at the origin of the coordinate system. CS is coordinate system. Second, determine the counterclockwise angle So determine the counterclockwise angle from, and I'll call that theta, from the positive x-axis to the vector. Then the x component is L times the cosine of that angle theta, and the y component is L times the sine of that angle theta. And the way people write components is different. I'm going to use this. So our notation in this class is going to be if that vector, so if this vector here is the vector u, okay, then I'm going to write it with the x component on top like this, the y component on the bottom, and square brackets like that. And it's not a fraction, so there's no line in between them. It's just sort of one stacked on top of the other one. People who don't use that notation most often use, so another common form that you would see would be that this vector is equal to L cosine theta times I hat, that indicates that it's in the x direction, plus L sine theta times j hat. So if you ever see that, that's what it means. That's the x component and the y component. Okay, this is an important thing to connect this vector component stuff that you haven't seen before to plotting points and dealing with graphs. So notice that the components of a vector are just the coordinates of the vector's head when its tail is at the origin. Okay, so yes, question.
Are you okay to use the like I and J?
Oh yeah, for sure. Yep.
What about the angle bracket?
The angle. Oh, to just show like a magnitude and an angle.
No, like in one of my other like math classes.
Yeah.
It was like an angle bracket and then the.
Oh yeah, and then a comma in between them. Yeah, any form that you're comfortable with, feel free to use. Yeah. So this thing about the relationship between vector components and coordinates. So if you have this coordinate system, and this is your vector. Let me change quadrants actually. Let me move it over to here. So let's say that's your vector, okay? And let's say that the coordinates of the head of the vector are -3, -2. Okay, or whatever form you're used to using for coordinates, you know. Then -3, -2 are also the components of that vector. The -3 is the x component of that vector, and the -2 is the y component. Okay. So all the calculations of vector components are the same as calculating coordinates of a point. So -3, -2 are the coordinates of the head. And the vector components. Okay, let's just do a couple examples. So let's say that we start with this vector that makes a 45-degree angle with the vertical. And it has a length of 5. What about units for vectors? I didn't mention anything about that. Vectors are just mathematical objects, so they don't have any units on their own. They can represent things that have any kind of unit. So, you know, like position vectors will have units of meters. Velocity vectors will have units of meters per second. And so on. The vectors themselves don't have any units. Okay. What? Oh, I got it. So now, what are the components of this vector? In first, let's say in the coordinate system that you're used to working with, you know, with x horizontal and y vertical. And then for part B, let's figure out what the components would be if you had a coordinate system that, so let's say this is the horizontal and vertical, and your coordinate system was at 45-degree angles from the horizontal and vertical. So this angle is 45 degrees. Okay, so we'll start with part A. That's the, you know, that's the one you're more used to plotting points and stuff in from your math classes. But there's no reason you couldn't have your coordinate system turned. And in physics, sometimes it's useful to have a rotated coordinate system like that. Okay, so the first one, we have this coordinate system. And just take the vector as it's drawn here and just like pick it up and move the tail to the origin of that coordinate system. So we know that this angle is 45 degrees. Okay, so what's the counterclockwise angle starting at the x-axis and ending at the vector? 90 plus 45, yep, so 135 degrees. So theta is 90 plus 45 equals 135. And so the vector components are, the length of it was 5, so 5 times the cosine of 135 degrees, 5 times the sine of 135 degrees. Can somebody with a calculator with sine and cosine in front of you punch that in? Oh, I have it here. I'm just used to not having it. Okay, so you get negative 3.535 and positive 3.535. Okay, so those are the components of that vector. Thinking, yeah. You'll want it in degrees for this class. Yeah. So thinking of vector components as the equivalent of, so think for a second about the coordinates of the head of that vector. Do the signs of those components make sense? Having a negative x component and a positive y component? Yeah, it's in the second quadrant, so that's what you would expect. Okay. It only works if the tail is at the origin, but as long as you move the tail to the origin, you can always check the signs that way. I think the most useful reason to check the signs of your answers is to make sure that your calculator isn't in radians and you think it's in degrees. Okay. Any questions about that first one? Okay, so now we're going to do the one with the rotated coordinate system. So now here's the horizontal. Here's the vertical. There's our x-axis. There's our y-axis. And where does the vector lie in this coordinate system? So remember, you don't rotate the vector around at all. You keep it what it was and just place it on that coordinate system. So where would I put this vector? What? So it would just, oh, I didn't give angles, so you don't really know, but did I? Oh yeah, I gave an angle here. Okay, so we know that the y-axis there is pointing in exactly the same direction as the vector. So if I put the vector into this coordinate system, it's just lying right on the y-axis, okay? So here's the vector. So if you start at our positive x-axis, the one we're using right now, and go to the vector, how many degrees is that? 90, yep. So theta is equal to positive 90. And so the vector components in this coordinate system are 5 times the cosine of 90, 5 times the sine of 90, and that's 0, 1, 0, 5, sorry. And I know you're not used to using rotated coordinate systems like this, but I mean, all you have to do to make it a regular coordinate system is turn your head a little, you know? So if you think of the coordinates, if you think of those being the coordinates of the head of that vector, does it make sense that those are the components of the vector? So the question is 0, 5, are 0, 5 the coordinates of that point? Yeah, it's just, it's not, it doesn't have any x value and it's just in the positive y direction. Okay. By the way, you can also come up with the angle by going clockwise and calling it a negative angle. So you can also go clockwise from the positive x-axis. And use the negative angle. So let me show you how that works with one of these. So let's go back to part A. So if I started the positive x-axis, we went counterclockwise 135 degrees. Okay. Now let's get there from the positive x-axis going clockwise. So you go 90 and you'd be going straight down. Another 90 gets you to 180 and you'd be straight to the left. So we're at 180. And another 45 gets you to the vector. So it's a clockwise angle of 225. And so since it's clockwise, you'd call it negative 225. And so if you entered this into your calculator, 5 times cosine of negative 225, 5 times sine of negative 225, it looks like a totally different answer you're putting in, but the way sine and cosine work, it gives you the same thing. Okay, so you can go negative or positive. It's your choice. Just remember, if you go clockwise, remember you have to call it a negative angle. Okay, once you express a vector in its component forms, once you express a vector in components, there are 3 calculations we're going to do in this class with vectors. Calculations we'll do. The first is adding 2 vectors together. The second is multiplying a vector by a number, multiplying a vector by a scalar, it's called. So that just means a number. And third, calculating the magnitude of a vector. Okay, so I'm just going to go through these 3 calculations. I'm going to talk about what it physically means to do these things. I'm going to talk about how to do the calculation with the components. And then it turns out that the sort of physical geometric meaning and the component meaning are the same thing, which I guess is pretty important when you're talking about a kind of math calculation. Okay, so adding 2 vectors first. Who's sick of this? Anyone yet? Everyone likes it still? Okay, good. I know like the parts where all we do are just doing mathematical stuff and we're not even really, you don't even know how it's going to relate to the class. It just gets really old really quick. But we got to do this, and then I'll try to be clear when with like applications when we go from this to the physics stuff. Okay, adding 2 vectors. So the physical meaning, first of all, of adding two vectors, or the geometric meaning, is think of the vectors as lengths of a journey, you know? So treat the vectors as legs of a journey. The sum of the vector is just the straight line of where you end up. So the sum of the vectors is just the vector from the starting point to the ending point. Okay, so like for example, if you're adding this plus this, think of each of these as like a leg of a trip. I'm just doing this so you okay, so if you're taking a trip and those are legs of the trip, you have to do one first and then you do the other one. And the sum of the vectors is just the vector that goes from where you started to where you end. So that red is the sum of those two vectors. What do you think would happen if you started out going the other way first and then you like flip the order of those two things? Same answer, yep. So the order doesn't matter when you add vectors. You would get that same red arrow either way. Any questions about that? Yes? Because think of it as like the arrow is pointing you where you go on the trip. You know what I mean? So you start out here. Can you see my cursor? And you walk in the direction of the arrow. You know, start here, walk in the direction of the arrow. Then you walk in the direction of the other arrow. And then the sum is just the straight shortcut from where you started to where you ended. If it was pointed down, it would be going from the end to the beginning. So it would be like going home after, you know? So that would be a negative of the vector. Any other questions? Okay, order doesn't matter. If you have the components of the vector, at first it doesn't seem totally clear why this is the same thing, but it is, as that geometric thing I just showed. If you know the components of the vector, or of the two vectors, then if you're adding the vector AB and the vector CD, the sum of those two has an x component that's just a plus c. You just add the two x components together. And a y component that's just b plus d. And those are the components of the sum of those two vectors. And so let me show you an example of doing this. I'll do it with the components, and I'll try to do it sort of carefully with geometrically, and maybe it'll sort of show you how these two things end up being the same. So for example, if you're adding the vector 5, -5 to the vector 0, 4, the sum of those two vectors is 5 plus 0 for the x component. -5 plus 4 for the y component. And so you get a vector that's 5, -1. So geometrically, it would go like this. If you have, so if here's your coordinate system, and here are your 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so your first vector is this. Okay, and to add it, you add the second one. You start the second vector where the first one ended. So that would be 0, 4, and you would end up here. Your resultant vector, your sum vector, is this. And the coordinates of that red vector, the coordinates of the head of that red vector are 5, -1. So whether you do it geometrically, just carefully with lengths and angles or whatever, or you do it with components, it'll give you the same thing. Any questions about that? Okay, well, let's just stop there. So in the lecture videos, it'll show you how to multiply by a scalar and calculate the magnitude, but you can break it up a little when you're watching the videos. So let's do the quiz now and just call it a day.